In this video, I will introduce a family of series, alternating series, which are easy to work with, and I will explain the theorem that justifies why. First, the definition. A series, an infinite sum, is alternating when every term times the next term is negative. What this simply means is that if a term is positive, then the next term is negative. And if a term is negative, then the next term is positive. So the terms I am adding alternate between being positive and negative. It doesn't matter which one I start at. For example, here is probably the best known alternating series. The sum from n equals 1 to infinity of minus 1 to the n plus 1 over n. The signs that change from positive to negative, we normally represent them by minus 1 to the n or minus 1 to the n plus 1. Let's see what the first few terms here are. When n equals 1, I get 1. When n equals 2, minus a half. And then plus a third, minus a quarter, plus a fifth, minus a sixth, and so on. I'm going to prove that this series is convergent. And in the process, we will actually see that a much larger family of alternating series are convergent, all of them. And I'm going to do this directly from the definition of series or infinite sum, which is as a limit of partial sums. Let's see what the first few partial sums for this series are. The first one, S1, is simply 1. Then S2 is 1 minus a half. Then 1 minus a half plus a third, and so on. So by definition of series, what I have to do is construct this sequence of partial sums and then see whether it has a limit. I'm going to argue geometrically. I will draw a picture for all these partial sums and see what I get from there. I start at 0. First, I add 1. Then I subtract a half. This is not going to be at scale. Then I add 1/3. Since 1/3 is smaller than 1/2, I'm going to end up somewhere between S2 and S1. Now I subtract 1/4. Since 1/4 is smaller than 1/3, I'm going to end up being between S3 and S2. And I keep going. Based on the picture, it looks like this sequence of partial sums is going to be convergent. I'm going to end up having a limit somewhere in there. What we've gotten is that these partial sums are ordered in a specific way. The even partial sums are ordered like this. And they are all smaller than the odd partial sums, which are ordered like this. I obtained this string of inequalities from the picture, but I can prove them algebraically if necessary. Every even partial sum is smaller than the next one, because to go from an even partial sum to the next, I have to add something and then subtract something smaller. The same argument tells me why every odd partial sum is greater than the next one. Then every even partial sum is smaller than the next odd partial sum, because I go from even to odd by adding something positive. And then I go from odd to even by adding something negative. So I can accept this string of inequalities. Now can I go from here and use it to prove formally that the sequence of partial sums must have a limit? I'm going to look at the sequence of even partial sums and the sequence of odd partial sums separately. What we've proven is that the sequence of even partial sums is increasing and also is bounded above, for example, by S1. So it's monotonic and bounded, and therefore by the monotone convergence theorem it will be convergent. But the very same thing applies to the sequence of odd partial sums. That one must be decreasing and is bounded below by S2. So by the monotone convergence theorem I conclude that both are convergent. However, I cannot stop here. This doesn't guarantee yet that the full sequence of partial sums is convergent, because the even terms may be having one limit and the odd terms having a different limit. I need to justify those two limits are going to be the same. So let me give names to those two limits. How do I prove they are the same? Well, I know how to write a relation between the even and odd partial sums. I can say that any, say, odd partial sum is the previous even partial sum plus the term I have to add, which in this case could be 1 over 2n plus 1. And now, if I think of this as 3 sequences with n as the index, this has a limit, and so does this. So I can use the limit laws. And I conclude that the limit of the sequence of odd partial sums, that's b, equals the limit of the sequence of even partial sums a, plus the limit of the term, which is 0. And so the even and odd partial sums converge to the same number. And I want to say from there that therefore the full sequence of partial sums also converges to the same number. To do this, I need to use a technical lemma, a general result that is true for all sequences. If I have an arbitrary sequence, if I assume that the sequence of even terms and the sequence of odd terms, those are two separate sequences, if I assume those two are both convergent with the same limit, then I can conclude that the full sequence must also be convergent to the same limit. This can be proven directly from the formal definition of limit of a sequence. I won't do that here. But I apply this result to the sequence of partial sums, and thus I conclude that our original series is convergent. I have not only proven that the original series was convergent, because the same proof is going to apply to a large family of alternating series. So in fact, I have proven a more general theorem. Let me go back to the proof, and I'm going to look at exactly which properties of the series I used. And then I'm going to write those properties as hypotheses, and I will have a new theorem in which I can conclude that under those hypotheses the series is convergent. What have I used? First, I've used the fact that the series was alternating. And just writing it this way doesn't guarantee it's alternating. I have to say that, of course, the terms I'm calling Bn are positive. I don't care where I start. An alternating series is the one where I can separate it as a sign that alternates times something positive. So this just means the series is alternating. Second, I needed the sequence of partial sums to look like this. I add something, I subtract something smaller, then I add something smaller, I subtract something smaller, and so on. That's what guaranteed that I had this string of inequalities. So I need the terms that I am adding and subtracting to be getting smaller. I need that sequence to be decreasing. And third, just those two properties are not enough. Those two guaranteed that I could conclude the sequence of even partial sums and of odd partial sums were convergent. But I need to prove those two limits were the same. And in the final step, I use the fact that the limit of the terms I am adding and subtracting is 0, that converges to 0. So that's the third hypothesis. And that's it. Whenever I have an alternating series, a series with those three properties, I can immediately conclude it is convergent. It applies to a lot of series. For example, I could look at the sum from n equals 2 to infinity of minus 1 to the n over ln n. And yep, it satisfies 1, 2, and 3. So by the alternating series test, it must be convergent. To conclude, alternating series are nice for more than this reason. Not only it is sometimes easy to check that they are convergent, they are also easy to estimate. That's a topic that is important on its own, and it deserves its own video. So I will leave that for the next video.